Hello, good morning.
Good morning, sir.
Hello, can you hear me, sir?
Yeah, yes, sir. Yes, sir.
Hello.
Yes, sir. Yes, sir. Yeah, am I audible, sir?
Yeah. This is Senthil Kumar here. I've joined once. You say okay, we can start, sir.
Yeah, just 2 minutes, sir.
Yeah, sure.
Hello, sir.
Hello.
Sir, can we, sir, host is there, sir.
Hello.
Ma'am, can we get yesterday's afternoon session material? Ma'am told she will share it. Can we get it?
Yeah, yes, madam. I will share it, madam.
Okay, through WhatsApp group or how it will be, sir? Through mail or?
Through mail, madam. Through mail, all the PPTs, all the documents, whatever the documents that they have given by the resource persons, that I can share in, madam.
Okay, sir. Thank you.
Okay, madam.
Hello.
Hello.
Yeah, good morning, ma'am.
Good afternoon. Welcome back. Day 5, session 2. Right now, I welcome all the participants for day 5, session 2. Session was handled by Senthil sir. Associate Professor Amritha, Coimbatore. Session title is Hands-on Object Detection and Tracking, Optical Flow Algorithms. So now I request Vijay sir, please introduce the speaker to the participants. Vijay sir, over to you, sir.
Yeah, thank you, ma'am. Myself, Dr. Vijay Ravan, working as Associate Professor in the Department of ECE, Vignan University. I am so pleased to be with you all today and to have a chance to introduce our eminent resource person, Dr. T. Senthil Kumar, who is working as an Associate Professor in Amritha Vishwa Vidyapeetham, Coimbatore, Tamil Nadu. Sir, area of interest are video surveillance, deep learning, cloud computing, video processing, wireless sensor networks, big data computing, and embedded automation. He has received a appreciation in Indian Express for agent-based programming in banking domain, as well as SAR has more than 25 publications in reputed journals as well as conferences. He is a part of funded project with IBM, DSD, and Ministry of Tribal Affairs. We welcome you, sir. Senthil, sir.
Sir, thank you, sir. Thank you.
Yeah, we welcome you, sir.
Yeah.
So kindly take over the session.
Yeah, thank you, sir. Thank you.
Thank you so much. Thank you.
Okay, so thanks to you all, and we'll start with the session. Thanks to HOD of C department, and thanks to Vijay Raghavan, sir, for giving the opportunity. I've shared my screen. Hope you are able to see my screen, sir. Hello.
Not yet opened, sir.
Now is it okay, sir?
Yes, sir. Jupyter notebook.
Yeah, fine. Okay, thank you. So we'll start. Okay, to each one of you, I'm T. Senthil Kumar, as the members have introduced about me. 1 second, I will move this down. Okay, so it is like we would talk to you more about today on optical flow with respect to objects, right? And with my expertise, why I am called, there's a coincidence. I did my PhD in area of video processing from Anna University, Chennai. And from then, I have PhD scholars who work on video analytics. So we are trying to solve problems with related to video type problems, where we are trying to address the possibility of using machine learning and deep learning. And the backend or in the core, we are trying to use all the image processing challenges. Sir, you are able to see the screen? Hello? Hello?
Yes, sir.
Yes, sir. Yes, sir.
Thank you. Please put your questions in the chat box. I will also answer to your questions. Okay. Right. See, whenever you are given any problem that you want to solve with respect to a video or image, the first question you should ask is like, does that problem actually require understanding of motion of the pixels? So you would have heard from the speakers, what is pixels, what is an image, and so on, right? What you call it as a motion. For example, if you see an image that I'm showing on the screen, this image has got a lot of cars which are there. So if I ask anybody, what do you want to analyze? Some person would say that I'm interested in counting the number of cars. So one person would say that, no, I'm interested in knowing which car is moving faster. The third person would say that, okay, can I come to a conclusion saying that there are two cars which are close to each other, but I would like to know whether the cars are falling under the same category or not, right? Whether they are Hyundai or they are Santro or Mercedes-Benz and so on. So given an image which is there in front of you, the first question you would ask is, can you analyze the data with the image, or you need a video? If I ask you a question like, if I want to know whether the car is moving faster or not, then that case you will say that I don't need an image, I need a video. Only with a video I can conclude that whether the car is moving faster or not. So the moving pixels is a challenge. Okay, so the first point I'm keeping to each one of you is the moving pixels. So what are moving pixels? Which changes, right? For example, if you look at a human face, the face is captured stationary. There is no movement, right? But if you capture it as a video, you would know that, okay, your face is moving. It is not that your face is moving, it is because the pixels are moving. So if you can find out the moving pixels together and connect them and say there is something happening in the particular video, or in the image, there lies your problem. Your problem would be either a project, or it would be a research, or it would be a proposal that you try to take up, right? So the thought process here is, when you want to take something as you want to detect, right, there are two answers to it. One answer would be is like, are you interested in detecting an object which will change the shape or which will not change the shape? So for example, if you ask like, will car change shape? No, car will not change the shape, right? But if I ask you, will humans change the shape? Yes. When you are, let's take, you are walking, not all times you walk in the same pattern, right? So you're walking maybe a little straight, or somebody would say, no, no, I bent my head and walked. So the moving pixels are changing. So the moving pixel regions, when they change, you can actually categorize them into two type of objects. One object would be a rigid object, and second one would be a non-rigid object. So the base understanding is, a rigid object means it will not change shape. A non-rigid object means it will change shape. So if I ask you an example, if wherever you are sitting now, you look around, you will say, I have furniture, they don't change shape, so it is called as a rigid object. I see humans, they will change shape, okay, so it is a non-rigid object. I see a bird, it will change shape, right? Because when it flies, the shape of the bird is different. So you call it as a non-rigid object. So the first thing that you have to understand is like, given something that you want to analyze, am I going to look at a rigid object or a non-rigid object, right? Now, once you have found it, then the next question would be is like, what are you interested in analyzing? Like, for example, if somebody says that I'm just moving my hand from left to right, then my system should be able to see the movement of the hand. I think people should be able to understand, right? If you move your head, right, from left to right, you are interested in knowing the movement of the head from left to right. So what you are interested in and finding out is the biggest challenge. So if you can find that pixels, then you can actually track the pixels. Please understand, right? That's why in all the image processing solutions or video processing solutions, we talk about two basic steps. One is detection of features, and next is tracking of features. So feature detection, feature tracking. Without feature detection, feature tracking, there is no possibility to develop any problems, solutions, right? So please make a note. Now there are two more keywords in front of you, feature detection, and next is feature tracking, right? Now, when somebody says, I'm interested in detecting a feature, then the question would be is like, what type of feature you are interested in detecting? Somebody would say, if I want to find only the red balls in the room, if I ask people like, how do you find the red balls? They will say that wherever there is a red, I assume it's a red ball, right? So you might look at the color as a solution to find whether it's a particular feature or not. Somebody says, okay, can you find a ball which is square? Can you find a ball which is circle? In that case, I need to find a ball, then I have to find whether it's a circle ball or I have to find whether it's a rectangular ball. So there you're bringing shape. So features will fall into two categories. One category would be basically under a concept of low level feature. The other one would fall into something called as a high level feature. So a low level feature means which is simple to detect. A high level feature means it's hard to detect, right? Now, once you have found the features, then the next question would be is like, can you track the features? If you want to track the features, then the question would be is like, you need to find the moving pixels. So there it is possible to do it by using this very popular algorithm, which is called as optical flow algorithm. It's a very uh, uh, successful algorithm which people are using it everywhere. Even today, when you go to deep learning, no, people will say that I'm using deep learning with optical flow. So optical flow is one solution that is used everywhere. So what you do in this optical flow is you are trying to compare two images. For example, if I want to know whether the car is moving faster here, I need to go to the previous frame of the car and I have to know whether the car is at the same position or not. For example, if the previous frame also the car is at the same position, then somebody would ask you, what is your x-axis, what is your y-axis? So what is your x value and y value of the car? If the x and y value of the car is not changed, then you would actually immediately say that there is no displacement. When there's no displacement, automatically there is no speed, because what do you say is velocity? Velocity is defined as rate of change of distance with respect to time. So when there is no change in distance, there is no change in the displacement, automatically there is no speed on the car. So there you can conclude that when the car is a stationary car, or the car is moving faster, or the car is moving very slower, right? Now, you need to now come to this part and understand. So what is optical flow is? An optical flow will say that take consecutive images at different time at t plus 1. Compare these images. When you compare these images, if you can find the velocity of the pixels, what is velocity? Rate of change of distance with respect to time. Then that case, I can say that there is something called as moving pixels. Once I know that there is some moving pixels on the screen, I can find that moving pixels and track that moving pixels. Okay, so that's a whole concept of your optical flow algorithm. So your optical flow algorithm would say every time that it can actually find the moving pixels, and that moving pixels could be connected. So how do you actually talk about the moving pixels? Is you say that every set of pixels that are connected, you can call it as a patch. So when you say it's a patch, it means that patch at time t, patch at time t plus 1, have they varied or not, right? So this will take you to two constraints. First constraint is something called as a brightness consistency. What is this brightness consistency? Is like we will say that when you have pixels, right, the pixels as such will not change just because there is a brightness. Please understand this concept. For example, when you talk about the light source, there are generally two types of light source. One light source is an ambient light source, another is a non-ambient light source. What is ambient light source? You go and stand near the sun, right? Automatically, you are illuminated completely, right? That is an example of an ambient light source. An example of a non-ambient light source would be is like, let's take you're going and standing below a tube light, right? It is an example of a non-ambient light source because you will not get a uniform illumination. So the first assumption of optical flow will say that the brightness is not going to be a challenge. That means the pixels will not look different because there is a change in brightness, right? So now when you take this as an assumption, you can actually say the possible places where you can use an optical flow. One, as I told you, wherever you want to find motion of pixels. Second, wherever you want to track any objects, like you want to track a car, you want to track a human. Next, wherever you want to find any errors in the camera. You're using a camera, you're taking a video, right? But the pixels are having some disturbances because there's a camera jitter, right? Then next one, wherever you want to align images on the screen, similar to a camera mosaic. Wherever you want to do some 3D reshape reconstruction, like you see in movies, no, there'll be a 2D object. The 2D object as such will become a 3D object, right? So wherever there's a 3D object coming in reconstruction part, wherever you want to introduce special effects, right? There you can use this concept of optical flow. Now, if I ask you a question, where does the pixels move here, right? If I ask you, is the pixels moving, right? Now somebody would say, if there's an air, this all these leaves will start moving. When this leaves moves, this also will move. When this moves, this also will move. So the principle I'm keeping in front of you is when a pixel moves, it is not going to affect that pixel alone. It is going to affect the neighboring pixels together. When the neighboring pixels gets affected, the other neighboring pixels also closely gets affected. For example, when this neighboring pixel gets affected, this neighboring pixels also gets affected here. So finding this moving area of pixels can be found by using this optical flow algorithm. Now, look at this here, right? When you look at this, this is with respect to the previous image. You can see that there is multiple pixels which are moving together where the motion can be found using an optical flow algorithm. Now, look at this here. This is an example of a non-rigid object. Humans are moving, right? Okay. But I want to know the movement of the humans with respect to the other human. Can I find it? Yes, you can find it by using an optical flow algorithm. Now, when you are using an optical flow algorithm, you can track the motion of the pixels. What is tracking is you fix a pixel or a region of pixels and you find how the pixels are moving in the consecutive frames. That is what is called as tracking. Now, with respect to this game video, you can see that the motion part can be seen on the screen. You can see all these places there is some motion. That means this player is moving with this player. This player is trying to have some movement with this players. This player is trying to have some movement with this players. So an optical flow output will actually try to say you, where is the motion of pixels? If there is a motion of pixels around the region, then you can bring your thought process and say it can be clustered, right? Then you can say that all this has more motion, all this has less motion, all this has more motion, right? There you can bring your thought process based on the application and say, this player is not having lot of motion, this player is having emotion, this player is having emotion. Now let's take the game has a foul play. You know what is a foul play, right? Now they have a doubt whether the foul play is because of this player or this player or this player. From the output, anybody can conclude that this person is not moving. So anyway, this person would not have created any foul play. Maybe it is because of this person and this person, right? That's how you should look at optical flow. When you use optical flow, you can find the motion of pixels. There you can bring your thought process and see from the application and say how the optical flow can be used. Now, the next one is basically the correspondence problem, right? Now, if you see from the left side, a dice, right side also is a dice. Now, there's a movement of the dice, right? Little bit it has moved. Now, I'm interested in knowing where is this pixel in the next frame. Please understand, frame 1, frame 2. I want to know the frame pixel here, how it is appearing in this frame pixel, right? This goes to something called as a correspondence problem. So if I can find for one pixel, I can find for a group of pixels in the dice, right? So that is possible when you go for an optical flow problem. Now, the next one people should understand is optical flow is not about 3D motion. Some people usually convince themselves saying that if I have a ball, right, and let's take I rotate the ball in the right side direction. I think people can visualize. If I have a ball and I'm just rotating the ball in the right side direction, it gets rotated. After it gets rotated, again it comes back. Yeah. So that is an example of a 3D motion, right? Optical flow is not like that. Optical flow as such, we look at pixel movement only in one direction. So that's why we say an optical flow is not a 3D motion. The next one, can you find structure from motion? What is structure from motion is, let's take you are standing in a forest, right? And you see only trees and leaves. Suddenly the leaves are moving. Just because the movement of the leaves is there, based on it, you might try to conclude there is an animal which is hiding behind the leaves. I think people can understand what I'm saying. It can be a fox, it can be a tiger, it can be a deer also. But your thought process is just because the pixels are moving, I'm trying to connect the motion of the pixels. And based on the motion of the pixels, I conclude whether it is a tiger or an elephant or it is a lion. That is called as structure from motion, right? Now, this one is just for you to visualize how an optical flow will take a motion of the pixels. Assume here from the left side, you can see there's an object. The object is moving. The object is rotated. Now, an optical flow from the 3D representation will say that you will have an origin with respect to the rotation, right? This is your principal origin for the rotation. With respect to the principal origin for the rotation, when there's an optical flow, there's a movement only in one direction. As I can show you here, there's a movement only in one direction. But that movement will be related to the principal axis. Now, the same optical flow, when you take it in a 2D representation, what happens is this is how the pixels are moving, right? So you will be able to track the motion of the pixels corresponding to the previous pixel in the same frame. This is pixel 1, this is pixel 2. With respect to this pixel, I can actually find the motion of this pixel. With respect to this pixel, I can find the motion of this pixel, right? So your 2D representation for an optical flow will give you something like a circular ring pattern. As you can see on the screen, this is a circular ring pattern. When you take a 3D representation, it's not like that. With respect to the principal origin, it will try to have a movement with respect to the principal origin. So how you can define an optical flow as? An optical flow can be defined as an apparent motion of brightness patterns, right? Wherever there is a brightness, right, I assume that there is a change. What is a change? It corresponds to the motion of the pixels. So an optical flow can be defined as the projection of a three-dimensional velocity vector on the image. Why do you say it is three-dimensional velocity vector? As I told you, an optical flow motion can be a 2D motion like this, or an optical flow motion can be a 3D motion like this, right? It can be a 2D or it can be a 3D motion like this. So when it is in a 3D motion, then we talk about something called as a temporal component. What is temporal component? Is the time component, right? The same thing, if you relate from the definition here, you can understand it better. An optical flow is a projection of a three-dimensional velocity vectors on the given image. So left side, what you see is an image of set of cars. On the right side, what you see is an optical flow output based on the brightness. This is car 1, this is car 2, right? This car is little darker. You will find different velocity patterns. This car doesn't have different brightness. It has a uniform brightness. So the velocity pattern will be looking similar on the right side. Okay. Now, the next one that you need to start understanding is when you look at pixels moving from one frame to another frame, as I told you, this is frame 1, this is frame 2. Pixels are moving. One pixel here has moved to this region here. This is at time t, this is at time t plus dt, right? So now when the pixels are moving, right, it is possible that the brightness of the pixels remain the same. When you say brightness of the pixels remain the same, so what is the assumption here? Your value with respect to the brightness, right, with varying time will remain the same. That means a pixel 1 at frame 1 will have the same brightness in frame 2 for the same pixel, right? So now this is one point. The second point is you should understand here the pixel that you're seeing here has moved to this location here. So this location here we call it as x comma y. This location we will say it's having a displacement. So the displacement can be said as u comma v, right? So what you can say on the right side is you can say it as x plus u, y plus v, right? So x comma y, here it is x plus u comma y plus v. Okay. Any questions from the participants? Sir, any questions?
Actually, sir is in class, sir.
Okay. Anybody has questions?
Sir, no, sir. Chart, no.
No questions. Fine. Okay. So we assume the brightness from this pixel is remaining the same in the next frame also. So the brightness remains the same. This is the first condition with respect to optical flow. Now let's go to the next assumption. One second. Yeah. So mathematically, when you formulate it, you will say that you are shifting the location. So shifting the location means x and y value alone change, right? So when you write it in the optical flow chain rule, you will say varying value of I with respect to x, right? And next varying value of I with respect to y. And you will have the third component, the rate of change with respect to time. So an optical flow constraint equation will be written as like this. First component will have the change for x, change for y, and change with respect to time. So now we have finished the first problem, which is a brightness constraint in optical flow. Now we are going to the second problem called as an aperture problem. What is this aperture problem is? The aperture problem says human vision capabilities vary, right? For example, let's take you are looking at an object. When you go closer to an object and see, and you come far away from the object, your understanding is your eye lens has an inherent capability to zoom in the details when you look at the object closer, and it has a capability to zoom out the details when you come out from the particular object, right? So the same thing we are looking at from the optical flow also. This is something called as an aperture problem. What is aperture problem is? An aperture problem says in irrespective of the object seen closer or the object seen far away, the motion of the pixels remain the same. So how do you conclude it? That's the next question. So here we assume the change of x as u, change of y as v, right? And similarly with time as it. So based on it, we write a single equation saying Ix, that is gradient of x into u, gradient of y with respect to v, plus I suffix t, that is this one, will be equal to 0. This is called as a horn and shunt optical flow equation. So an optical flow algorithm has two categories. One category is called as horn and shunt. The other category is called as Lucas Cannon. So what you see here is horn and shunt optical flow equation. In this, you should understand you have two values which needs to be calculated. One, change of x, another is called as change of y. Time will be known because if you take a video, no, you will say it is a video which is captured at 250 frames per second. That means you know how many frames will be captured in 1 second. So the change with respect to time is known, but the change with respect to x, that is u, and the change with respect to y, that is v, is not known. That is why we say this is one single equation, but it has got two unknowns, one for u and another for v, right? Now, we will have to realize how does it work with respect to a given date. Now, let's take with respect to a 1D dimensional case, right? When you take it's a one-dimensional case, we assume that the brightness constancy is a first constraint because I'm repeating to each one of you. We have two constraints to be checked every time. One is brightness and second is aperture quality. Now we are talking about the brightness consistency. It says that across the frame, a pixel seen in first frame will have the same brightness in second frame also, right? That's the thought process. So if you're going to express it, you will say f of t is given as I of x of t comma t, right? So here we assume that there is no change in brightness with respect to time, right? So we will say change of f of x, right, with respect to t will be as 0. Now, when you expand this and write, you would say that the inner component will be rate of change of x with respect to t, right? And the other component you will have is rate of change with respect to time alone. Since we talk about one dimensional, it means that we are considering only x. Please understand, 1D means what? Only x-axis. We are not considering y-axis. So the rate of change with respect to y will not compute, right? This is called as Ix. This is V. This is IT. Fine. Okay. So now, if you take IT to this right side, it will be minus I suffix T, right? So left side, what you will have is you will have Ix into V. So V can be given as minus IT divided by Ix, right? This is optical flow in 1D case. Now we can see the output as you visualize in the graph. If you assume another image as I of x with time t plus 1, what has changed in this velocity component is only the x value. What is v here? V is nothing but minus I suffix t divided by I suffix x, right? Now, if you take the derivative for it, you need to look at the spatial derivative. So the spatial derivative with respect the spatial derivative with respect to t would be given as rate of change with respect to t, right? With a given pixel as a reference, the pixel reference is p here, right? Value of v is similar to what we see from the previous slide. It will be minus I suffix t divided by I suffix x. So what has changed from this slide to this slide? In this slide, we are representing v as a vector. Why? It has a direction. Please understand the concept. So it is no more pixel. It is a pixel which has a direction because when you throw a ball can move in any direction. So you cannot just say it is just moving. It is having only spatial coordinates. No, it has a direction component also. So here in this slide, we are representing v as a vector, right? Now, when you keep improving this, we would actually say we are trying to compare the velocity of the pixel from the previous frame with the current frame, right? So there you are talking about something called as a temporal component. So what is temporal component is? How much velocity the pixel is holding in the particular time interval. So when you say that I'm able to find how much velocity the pixel is able to hold in the time interval, I will be able to get the temporal derivative, right? So what will be the temporal derivative? The temporal derivative will say, when you want to find the velocity of the current pixel in the new frame, it can be given as the velocity of the pixel in the previous frame, right? Minus I suffix t divided by I suffix x. What is I suffix t? This equation is, this equation is nothing but the velocity with respect to the current pixel. Please understand the concept. Now we are in frame 2. I want to know the velocity of the pixel in frame 2. So what I can do, I can take the velocity of the pixel in the frame 1, which is V previous, and add it with the velocity of the pixel in the current frame. So the equation for the velocity of the pixel in any frame is given as minus I suffix t divided by I suffix x. So naturally my equation will be given as the current velocity of the pixel is given as velocity of the pixel in the previous frame minus I suffix t divided by I suffix x. Now, we are now going from 1D to 2D. Right? Okay. 1D
Sir, voice cut అవుతుంది sir. Sir. Sir, voice cut అవుతుంది.
along x. 2D means along y.
Sir, voice cut అవుతుంది sir. Senthil sir. Hello. Senthil sir.
So in this equation,
Hello, Senthil sir.
you can find
Sir, no voice, sir.
Sir, unable to hear. Hello, sir.
Senthil sir. Senthil sir. కట్ అయినట్టుందా అదేంటి డిస్కనెక్ట్ అయింది డిస్కనెక్ట్ అయ్యారేంటి సార్ Senthil sir. అక్కడ టైప్ Senthil. SCN. Maybe network issue.
Hello, madam.
Sir, please, sir.
Okay, madam. Okay, madam. We will wait. When the test will conducted, madam?
Test, yesterday all of you requested at 7:30, na?
Yes.
7 to 7:30 you asked, na, yesterday.
Yes, madam.
We will go with that only. 4 to 4:30 we are having valedictory. With that we will close today. Again at 7 o'clock we will have the exam.
7, madam?
7 to 7:30, sir, half an hour.
Okay.
Okay, sir. 20 questions, sir, 25 marks, all are multiple choice.
Okay, madam.
Okay, sir.
How the certificates will be given, ma'am?
You are going to get from the Atal website only, madam.
Okay.
For that we have to upload 5 days attendance as well as the marks, exam marks. After we uploading the attendance and marks, you have to give the feedback form. Everybody should fill the feedback form from
Yes,
the
yes.
Atal site, madam. Then you will get the certificate.
Okay, okay, okay.
I think 2-3 days it will take, madam. Today exam over means we are
Hello,
going
madam.
to
Madam.
submit.
Yeah, yes,
Madam,
madam. Yes,
madam.
madam. It will take 3-4 days time, madam. After
Madam.
completion of,
2-3 days we
after
need.
completion of uploading the attendance and marks and feedback, after that they will take 2-3 days.
By the end of next week you will get.
Yes, madam. Yes.
Okay,
Hello.
sir, thank you.
Hello.
Hello.
Ma'am, when we will receive the test link, ma'am?
Test link before 5 minutes. That is 6:55.
6:55.
Yeah.
Okay, ma'am. Okay.
Madam,
Amma, please.
madam, it is not possible for us, madam. 6:55. Yesterday also we opted for 4:30 p.m. madam. Actually, we will be in the bus, madam, at that time.
But all of you told in the chart 7.
Yesterday, actually, even I have typed it as 4:30 p.m. madam, but it is not considered because of less majority.
You only
After
telling
8
na,
also,
madam.
it's okay, madam. Madam?
What, madam? What you are telling?
Hello.
After 8 o'clock, is it possible, madam, to conduct the exam after 8 o'clock?
Madam, can you hear me?
Yeah, madam.
Madam, can you hear me?
Yes, sir. Yes,
Please,
sir.
please, sir.
Yeah, shall I continue, please?
Yeah, sir. Yeah. Go ahead, sir.
Yeah, sorry to you all. I had a network
No
problem.
problem,
So
sir. No
it's
problem,
okay.
sir. Carry
Yeah,
on.
please don't mistake. Okay. See, the whole idea of optical flow is to analyze the moving pixels. So what we saw was in the tracking in the 1D case. Now, when we go to 2D, you'll find one more component, which is your y-axis, because we need to know the moving of pixels both along the x and also the y-axis. So there you will get two components that you need to find. One is actually along your x-axis, that is u, and the other along your y-axis, that is called as your v here, right? Okay. So there needs to be two unknowns that needs to be predicted. One unknown is along your x-axis, which is u, and the other unknown is nothing but your v, which is along your y-axis, right? So this equation will be slightly challenging compared to the previous one, because in this one, we need to find only... Hello? I think some people's audio you will have to mute, please. Hello? Hello? Okay. Along the x-axis, you are finding along u, but when you come to this equation of a 2D tracking, what happens is you need to find the equation with respect to u and also v. So this is slightly challenging because you get two unknowns. Now, with this challenge, we can now move on to see how it can be solved. Now, the approaches to the solution is, please try to understand, we need to find the value of u and the value of v. For that, we have two algorithms. One algorithm is your Horn and Schunck algorithm. And next algorithm that you have is nothing but your Lucas-Kennard algorithm. Please make a note, Horn and Schunck, and next one is the Lucas-Kennard algorithm. Before we move on to the algorithm, let's see some possible things that you should understand, because this will be helpful when you look at a real-time problem. The first one that you can see here is a Barber pole illusion. What is this Barber pole illusion is, if you take this object and let's take there is a movement around this origin. This is something which you can similarly refer to a fan. If you see a fan in a room and you see that the fan is rotating, there's a spindle to the fan. The spindle to the fan can be called as your z-axis, right? Similarly, here, this object is having a rotation around your z-axis. The rotation is like this, right? Now, normally when you look like this, you will assume that the pattern is keeping on moving, right? But in the real part, what happens is an optical flow will assume the movement to be like this. The pixels are moving upward, right? So this one is called as your Barber pole illusion. Now, the next one that we need to talk about is the aperture problem. If you look at this region, right? Look at this here. Now the question here is like, if there is a movement of pixels, the movement of pixels can be actually along the edge of the pixel also. Suppose you are tossing a ball. The ball is tossed around the corner. Around the corner when it is getting tossed, the edge of the pixels is moving, right? So this is the next challenge that we will have here. But when you take the aperture problem and consider it here, right, you will be able to find that the movement along the edges also can be seen. Let's see how we do it. So you can conclude that an aperture problem in real time can be considered equivalent to what you see in the Barber pole. In the Barber pole, what we are saying here, there's a movement, the movement is like this, but in reality it is like this, right? Okay, the same aspect you can consider with respect to the aperture problem. Now, with this as a basis, the discussion will now go and start understanding about the normal flow of the movement of pixels. Now, the pixels are moving, right? So at any point of time, your answer is what? There are three things. One is gradient of x into u plus gradient of y into v plus gradient of along the time, change along the time is equal to 0. So the equation can be written as ixu plus iyv is equal to minus it, right? Now the similar way, you can look it as a line equation like this. So this is a line equation, ixu plus iyv plus it is equal to 0, right? Now if you look at what is your normal flow, what the normal flow can be found by looking at a point from the origin perpendicular to the line, right? So you are drawing a line perpendicular to this from the origin. When you draw a line perpendicular to this from the origin, what you will be getting is you will be able to get two components. The one component will be calling itself as the variant with respect to I, that's your gradient part, right? Which you can mention here. So when you say gradient of I, it means that rate of change along X and rate of change along Y. The other one which you will be getting is I suffix t, right? So this will be the main part of the equation here. This is the original equation, right? Now you want to know the gradient along x and y. You replace it as gradient of I transpose into u will be given as minus I suffix t, right? So here, what is this capital U? That's a bold U that we mentioned as U will have two components. One with respect to U, that's a change along x-axis, and next is with respect to V, that's a change along your y-axis, right? This is with respect to the normal flow of pixels in a given video. Now the same thing, if you look at from the aperture problem perspective, this is the region of pixels that you want to visualize, right? And the pixels are moving along this region. Now the aperture problem will say that you need to look at the moving pixels, but you need to look at the moving pixels along the direction they move. This will enforce a new constraint, which is called as a gradient constraint. So what will gradient constraint will say is, this is my principal equation, but this can be written as the gradient of I multiplied by u vector. What is this u vector here? U vector will be nothing but the change with respect to x, that's your u, and change with respect to y, that is your v. Now, if you take the same thing with respect to the equation that we started, the equation that we started here for the graph, you can see here, you have moving pixels, you have a line which will actually have the intercept along the x-axis as u, intercept along the y-axis as v, right? And we found what is u and what is gradient of I. Now, if you take this as an input and look at this one, we will actually introduce the new equation for u, right? This will be the new equation for u, which will be the equation which considers the aperture problem also. See, when you look at all this, you'll get a doubt, why should I consider condition 1, condition 2 like that? This is a natural scenario. When you take an object, you should assume that the brightness of the object might vary, right? The movement of the pixels may be along the y-axis. That will introduce an aperture problem. For that, what is the equivalent equation you need to consider, right? Now, when we move on to the next part, this will give you the equation with respect to both the aperture problem and the normal flow. How does it give us? Along your x-axis, you have u. Along your y-axis, you have v. The intercept along your x-axis will be ix by iy. This will be it by iy. Why do you say here? When you say with respect to v, we are talking with respect to the time component, right? So we will say I suffix t divided by I suffix y. And the line that you draw from the origin to the line, that's your intercept of x and y axis, will have a value as distance as d, right? And any point along the line will call itself as u dash and v dash, right? So your assumption is at every, but the moving pixels can be anything along this u dash and v dash along the line. Please understand the concept. The pixel may be here, 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 here. but anywhere you will call it as only U dash and V dash, right? So U dash V dash will call itself as a normal flow, right? And from there, you will call that as a true flow also, right? So this will have two components. One will be the normal flow, which you see here, which is D. And next one is a parallel flow, which is called as your P. Please understand the concept. Normal flow is D, parallel flow is P, right? Now, normal flow can be computed. What is this normal flow is? When you say a ball is moving from left to right, from one frame to another, you will always conclude that I know that the ball is moving at this speed. I know the pixel of the ball in the particular frame, that is frame 2, right? Because I know the speed of the ball. So there it's a normal flow. Parallel flow is different. Parallel flow, as you can see here, for every movement of the pixel, there may be an supportive pixels also which will move. So parallel flow cannot be computed. Please make a note here. Parallel flow cannot be computed. What is parallel flow here is P, right? Now, this to make it happen, there are two approaches that are there in optical flow. One is called as Horn and Schunk, and next is Lucas Canning. There is also an approach from this person called as Skunk, right? Let's see these approaches. First approach that is being proposed is, if you have two pixels which are there as part of a rigid object, right? Let's call, right? We can compute the normal flow for it. What is normal flow? Please keep this recap. This is normal flow, perpendicular. There is a parallel flow, which is P. The normal flow can be given as V suffix N1 and V suffix N2. So what is this V cap is given as? V will be given as V and U, right? Now this equations for this would be written as saying there are two possible flows. Please understand, one is like this, Vn1, and other is Vn2. Okay, one second. So our assumption is, if there are two pixels moving adjacent to each other, for one pixel you have a normal flow as V suffix N1. For the other pixel we have a normal flow as V suffix N2, right? So what is this Vn1, Vn2? It means that pixels at time t1 and pixels at time t2, right? So the two equations that you will get from here is this equation first, which will have I suffix t1. The second equation is I suffix t2. One second. Yeah. Now, based on this neighboring pixels, this person Skunk, he actually proposed an algorithm, and he said that if two neighboring pixels can move the same velocity, right? Okay. Then what happens here? It is possible that both the pixels will intersect at one point. It is something saying that, see, I have two balls. I'm moving both the balls from left to right. I think people can visualize. I'm moving a ball. I'm moving one more ball also from left to right. Both the balls are moving with the same speed. So what is possible is at one point, both the balls will intersect with each other. I think you can understand, right? So when you say it is intersecting, it means that both the pixels are intersecting with each other. So the solution here is, you can find the intersection points. There will be a set of points where they intersect. That set of points together can be called as a cluster, right? Now, how do you say that there is a large movement? Find all the possible clusters. Wherever there's a biggest cluster, which has got the motion of the most of the pixels, you can say that is a point where the motion is higher, right? That is a principle which was proposed by this person called as Klunk, right? So in this, you can see here, the cluster pixels are being connected together based on the velocity part, and this is a region where they have the closest motion, right? The next algorithm we are going to see is horn and skunk algorithm. What we have finished is skunk algorithm. Now we are going to horn and skunk algorithm. This horn and skunk algorithm, their approach is they propose a concept of something called as regularization, right? Okay. So regularization is connected to smoothness in image processing, right? So this process authors proposed two terms. One term is called as departure from smoothness, and next is error in optical flow constraint. What is this departure from smoothness is? This says that you can actually consider the variance with respect to u and v along x and y, right? And from that you can find e suffix s, right? Which is called as your departure from smoothness. The second part that they proposed is the error in optical flow constraint equation. When you say error, it is expressed as E. So there will be an error along X, error along Y. There will be an error along T, E suffix X, E suffix Y, E suffix T, right? Together, all these errors together will be called as E suffix E, as we can see here. So the challenge here is we are interested to find this two terms, that is departure from smoothness and error in optical flow equation, how much they affect on the original movement of the pixels. So there you together sum it, that is E suffix S plus E suffix E. So here you will find a parameter called as lambda. This lambda as such will actually be a parameter which will try to smoothen the value of E suffix E, right? So the equation will be given as E suffix S plus lambda into E suffix E. So Horn and Shunk in optical flow, they suggested we want to minimize the combination of these two, right? So further, what was introduced is, you go back to the previous one, what we wrote is we said the gradient of phi, right, multiplied by v vector plus I suffix t. Now we are talking with respect to Horn and Shunk, the same thing here, right? Here, they need to introduce this constants. What are the constants? One is the smoothness constant. What is smoothness constant? E suffix S. So E suffix S is being introduced, right? And next one that they introduced is the error constraint. What is error constraint? E suffix C. So Horn and Shunk resembles the previous equation, but together it has got two things. One is the smoothness constraint and next is the error constraint. Then the next is the energy component of the pixels. See, this is slightly hard to visualize, but I can give you a small example. Let's take you are seeing pixels moving, right? Every pixel has an energy. I think people will agree, right? For example, let's take a snake is moving on the road, right? And let's take the snake is moving on the leaves. Please understand, there is a set of leaves which is on the road. The snake is moving on the leaves. Now, once the snake is moving, based on the speed at which the snake moves, right, automatically the leaves also moves. So there is an energy component to the pixels. Please understand this and take it, please, participants. The energy component of the pixels will help you to understand how much it influences the motion of the pixels, right? If you want to get a more better thought, no, I would give you one more example also. The advantage of a snake, if you see, if you take a bigger box and put the snake will keep itself to the box. If you take a smaller box and put the snake, what it will do, it will also do the same thing. Only thing is like it will try to contract or reduce and it will try to keep it within the box, right? So the same concept comes here also, right? The energy component will be an important factor for the pixels. So an energy function is being proposed. What is this energy function is? The energy function is given as E of x comma y. This will have two parts. One, which will be u into ix, v into yy plus it, right? This will be a second order part, so it will be square plus lambda we saw earlier itself. It's a parameter multiplied by the same ux square plus uy square plus vy square plus vx square. This is called a CF, right? So next what we do is we try to differentiate E with respect to U. differentiate E with respect to V, right? I think people can understand. So here what we will be getting is, you will be getting as 2ix because you are differentiating only with respect to U, right? You will not get 2iy here. But whereas when you try to differentiate with respect to V, you will get 2iy, right? And this two parameters, that is Vxx, Vyy, will be the other parameter terms that will be arrived when you are trying to take E and differentiate with respect to V, right? And now the question is with respect to F. When you differentiate F with respect to U, right, you will be getting two terminals. One is Uxx and next is Uyy. This is called as your Laplacian of U. The Horn and Schunck algorithm will try to take the terms what we got earlier. You can see here, this is term 1, this is term 2. Okay, it will take the terms. There what it will do is, it will try to assume that the smoothness is going to be common. That is the pixels are moving in the same manner. So this one, right, will get eliminated. So what will come up is, the same equations will get rearranged and they will say the value of U and V like this. So the value of U would be given as U AVG, right, minus the other components that we are, right? And next is V will be given as V AVG minus IY into other components that you have arrived, right? So what is this UAVG, VAVG? Please understand here. This one is written as U minus UAVG. This part, right, is written as V minus VAVG. Now when you substitute it here, you will be getting UAVG and you will get VAVG when you are trying to find V here. Now, when you further expand this, your Euler concept can be used and you will get the new equations for change of U and next is change of V. Okay, so this is how Horn and Schunck algorithm works. So what we have seen right now is the theoretical part of optical flow algorithm. Now let's go to the practical part of doing the code. Now, when somebody says, I want to implement something like this to my application, so first step would be is like you need a programming platform. I think experts have already talked to you. So the common one would be is like you can use any framework. So I suggest people to use Anaconda framework. If you go to Anaconda, right, you get Anaconda framework. There you can download Anaconda and you can install, right? So once you download and install Anaconda, you will be getting Anaconda in your terminal. So you can go and open Anaconda prompt, right? You can go and open Anaconda prompt. This is your Anaconda prompt that I've opened. Now, the advantage of this is when you work with any third-party libraries, you can go and install in the Anaconda prompt itself. For example, if you want to install NumPy, you'll go and say pip install NumPy. Okay, so it'll automatically connect to the internet. It will install something. I'm saying very basic because I'm teaching as I learned the things, right? So now it will connect to the internet and it will install. So I usually suggest people to use Anaconda as one single one for running most of the applications. Now the next question somebody would ask is, see, I want to code, right? How do I code? So there the answer is like you can use Python. Python is a very good programming framework to code and run your application. So I suggest people also to go for Python. And in case you're going for deep learning, you can use Keras. Keras is a very good framework for running the applications. You can use Keras, you can use Theano, or you can use TensorFlow to run your deep learning applications, right? If you are not using deep learning, please do not use Keras or Theano or TensorFlow, right? Okay. Now it's connecting to the internet. Let it go on. Now, the next one that I want you to know is whenever you are trying to do anything with image processing, you need to use OpenCV, right? So if you go to the internet and type OpenCV, you will get OpenCV library. So please download and keep OpenCV for your application. Participants, all of you, please download and keep OpenCV for your applications. So if you're going to Anaconda, it becomes very simple. What you will try to do is you will actually go and you can actually directly install OpenCV. You can say pip install OpenCV hyphen Python. Automatically, it will install OpenCV in your system, right? If you miss what I'm saying, don't worry. If you go to your internet and there, if you type OpenCV, if you type pip install OpenCV hyphen Python, right? This is a command. Okay. All you need is one patience to work. That's all. So you have to type, copy this command. You have to paste it in your prompt. Automatically, it will connect to the internet. It will install. Now it's connected. It says NumPy is already installed. The same way, if you type pip install OpenCV hyphen Python, it will connect to internet. It will install OpenCV on your system, right? Okay. Now, once all is done, then the next question would be is like, I also want to write a code where my programs will run. Okay, that's the next question for everybody. There, you should actually take some data set that you want. So you need some good data sets for you to work. So there are a lot of data sets. One link that I usually suggest to people is outlier data set. If you go to internet and type outlier data set, you'll get a link which is from Stony Brook. This will have good data sets for you to work, right? This is one good data set for you all to work. Then the next one that you can actually take with respect to video data set is you can try to find some data sets which are in Kaggle. Okay, so Kaggle has some good data sets which you can work, right? If you go to Kaggle website, you'll find a lot of video data sets that you can work. You can download the video data set. After everything, if you find no, it's not very interesting, then solution is very simple. You itself capture your data set. For example, if you want to work on car, maybe if you have a possibility to take the live traffic data set, you can take the live traffic data set and you can work. Okay. Now, the next question would be is like, I want to write some code. I want to track the objects, right? Whatever I have. So OpenCV is very direct. You can actually use OpenCV for the application. A simple code, which I'm showing you here. We need OpenCV. So in the beginning of the code, we will say import CV2. The next, we want to load the video. So I have a video. I'm just saying CV2.video capture the video file name, right? The next is I need the parameters for detecting the corners, right? So I can use this function, which is DACT. This will ask you some parameter size. First parameter, most important, is a block size. So you can give the block size. You can give the minimal distance value. You can say what type of quality level you want to have and what is your maximum number of corners you're trying to work, right? The next one is it will ask you what are the parameters it needs to detect. So there you can actually say what is the window size, right? And you can say what are the other parameters with respect to the criteria that can be defined. All this are having good information on learning. When you go to the internet and type the keyword itself, you'll get the manual for it. Please spend some time on it. The next is we are trying to set the colors that we want to read. The next is what we do is we are trying to take frame by frame. So this line of code, what it will do is it will try to take the first frame. First frame means the first frame in the video, right? Then what we want to do is you want to find the features. For that, there is a method called as good features to track, right? There's a method called as good features to track. This is actually built on the optical flow algorithm. This method is built on the optical flow algorithm. You can just say good features to track, right? There you can actually take the frame that you have taken, right? And then next step, what we do is we'll mask the image, right? And then this is the most important part where we will call the optical flow. Just now I spoke to you for a longer time about Horn and Shank, then Shank algorithm, all that. All this will become simple. Here what we are trying to do is we are trying to read the frame Then we are trying to call the optical flow method. The method is called as CALC, optical flow PYR LK. This is an inbuilt method. Once you call this method, it will estimate three parameters, right? And that from that three parameters, it will be able to find out which are all the moving pixels. Once it is able to find the moving pixels, right, it will be able to track the moving pixels and it will try to show it on the frame itself. Frame means the given video that you're trying to work, right? And in the output, it will show you the frame, right? And it will show you the pixels as it is being tracked. Okay. So this can be run in one way. You can actually take it in your Jupyter and run the code. I'll share the code to the coordinators. Please collect it and run. Only thing you will have to make a changes. You will have to change the video file. Here you can give a video file that you want and rest of the things will run. It will show you the output, right? This will show frame by frame. That is the purpose. So first frame output, second frame output. Every time it will wait for 25 seconds and it will start showing the next frame, right? So the code will look very simple because here you are using only two things. You will be using only a method called as good features to track to get the features. Then the second method you will be using is CALC, optical flow PYR LK. And from the change in the code, you will have to go and change the video that you want to work. And this will work only when OpenCV is installed. So please make sure that in your Anaconda prompt, you have installed OpenCV Python. That means you type it as pip install OpenCV -Python, right? So once again, pip install OpenCV -Python. When you type it and press enter, it will connect to the internet, it will install. Now I've already installed in my system. So it says requirement is already satisfied. Right? So you want to run the code from Anaconda also, it is possible. This has got a Python shell, right? So let's take my program is called as my.py, right? So I can just go here and say my.py. Okay, right? So now there is no program like that. I'll show you that also. Maybe it might give you a thought process. Now I'm taking the code folder. This is my code. Okay, this is under D drive optical flow. So I will go to that. So I will go to D drive. I'll go to optical flow. Right now, when I go and see, I got this code. So I will say Python space the file. Right now, as such, it will run the code. So it will try to show the visual output. It will take some time. So now what it is trying to do is it is trying to take the video which is there. Then it will try to run by detecting the features. Then it will call the optical flow algorithm, right? And then it will try to show the output. It will take some time, but it will run. Okay. So that comes to the summary of my session. So what I have spoken to you is the understanding with respect to optical flow and how the optical flow algorithm works. And I have also explained you about how you can do the code with respect to the Python. It's a very good algorithm. Now, in case people are working something with deep learning like that also, now the approach is we are trying to use optical flow with deep learning, right? That's a new trend that's coming up. Showing me a small error. Okay. It works. You can try it on your systems. It will not be a problem. I think some library has to be installed. That's all. So that's it from my side. Any questions from the participants? I'll be happy to answer. I'll put my mail ID also in the chat box. Actually, we have a funded project from DST which we have completed, and this we have shared it in the Smart Space Lab. We have a lab called the Smart Space Lab in Amritha, where we have captured the data set and we have kept it. right? So if you want, you can download the data set from the Smart Space Lab also. Any questions from the participants? Madam, I completed my part. Any questions from the participants?
If you are having any problems, please interact with the sir.
Hello.
Yeah, thank you so much, sir.
I request the participants, please interact with the sir.
Okay, as I started from the beginning, I work on
Sir,
video.
nobody.
Excuse me, sir.
Yes,
What type of problems can be solved using these algorithms, sir? One question is there in chat.
Okay, any video based problem where you want to find a motion and take a decision. Okay, for example, if I want to know whether two people are fighting, let's take they are college students, right? The motion of the person's hand with other person's motion can be taken. Second, if you want to detect a fall, I want to know whether somebody is going to fall or not. So that can be solved. It's a fall detection problem. Third is like accidents, detection of accidents. Can I come to know that this car is going to hit with the other car if it travels at the same speed? There you can solve it using optical flow algorithm. Okay. Hope this would be helpful. Any place where motion can be used to solve, right? There you can use optical flow.
Sir? Yeah. Good afternoon, sir.
Good afternoon.
Sir, regarding funding proposal related to AI and ML, like a budget, like it is fully related with the programming and the data set, like where we can what are the things we can show under the budget?
Okay, actually from my limited knowledge, as much I understand what the agency says is they are not interested in you purchasing new softwares. So naturally you will have to go to Python, correct ma'am? Python, Anaconda, open frameworks you will have to use. But what you can actually put in the budget is you can actually ask for the hardwares. Like you can say computers is generally, you will show it from the college. Along with that, you can ask for computers which are GPU enabled. You can ask for one rack server, which is GPU enabled to run computer vision based application as part of your proposal. And you can ask for a Doom camera also, right? In case you're going to take live data and you're going to process. Because one Doom camera will cost around 2.5 to 3 lakhs. If this is going to be a proposal which you're going to write with thermal camera, you can add one thermal camera also. That will cost around 3 to 4 lakhs. This is how you can put the budget. Other than that, you can put the budget with respect to the human part. That is the JRFs are there, no man. For each of them, you can put the budget with the salary and you can write your proposal.
Thank you, sir. Thank you.
Yeah, thank you.
Sir?
Yes, madam.
Yeah, am I audible, sir?
Yes, ma'am, you are audible, ma'am.
Sir, good afternoon, sir.
Good afternoon,
Sir, I'm working on 3D image, like video processing, sir, in my project work.
Okay.
Actually, like I'm completely relied on the CNN and the RNN. Like whatever you taught me is object tracking without using those things. How I'm working on it. How it will be used in my own area, sir.
What is the type of data set you are working on?
Like it's a sign detection data set. Sir.
Sign language detection.
Yeah.
Am I right, ma'am? Right.
Yes,
okay.
sir. Yes.
Fine. See, now let's take a scenario like this. I'm just trying to make things better for my understanding. Let's take there is a Nepali, right? Okay, who wants to communicate his sign to you. Are you getting, ma'am? Because
yes,
you
sir.
don't
Yes,
know
sir.
Nepali
I'm
language.
here, sir. Yes, sir.
Yeah. So the person is moving the hand, finger, and the person is trying to say something. So the hand and finger, as it is being detected, your software will say it is a word, hello, hi, how, or like that. Am I right? So
yes,
that
sir.
case,
Yes.
you can actually do it as a gesture recognition, where
yes,
you are finally saying that it corresponds to the words.
Yes, sir.
Now, the question is like, if I want to know the translator is a good translator or not.
Okay.
Right? Or I want to know from your face expression whether you are able to understand it correctly or not. Okay. I can actually inform the person saying that you move the finger slow, you move the finger faster, for example, right? I'm just saying you. That
An
can
example.
be
Okay.
found by using the optical flow algorithm.
Okay. I do understand, sir, now.
If
So
you're
it's
not
about,
going to take
yes.
it, it's only
Yes.
images. The images are trained with the
Can I
CNN or
incorporate
RNN.
those algorithms in the CNN architecture? Because
Yeah,
CNN
yes,
architecture,
yes.
like,
Yes, yes. Now we have architectures which are based on optical flow with CNN.
can I have some examples, sir?
Yeah, it is there, ma'am. Maybe I will try to put some papers to the coordinator. I think that will
Sure,
help
sir.
you in that.
Sure, sir. Thank you, sir.
Sure,
Thank you
ma'am,
so
sure.
much. Yeah.
Yeah, yes. Ma'am. Actually, my scholars, they work on video analytics. One of my first scholar is working on detection of faces using deep learning. So
Okay, sir.
he's
Thank you so
completing
much,
his
sir.
thesis. So the next scholar is working on fire detection using deep learning. The third scholar is working on traffic detection on road using deep learning. So fourth and fifth person is started to work on deep learning with network analysis for malware detection. So I'm trying to strengthen myself with deep learning, so I can really give you some suggestions.
Thank you so much, sir.
Thank you, ma'am. Thank you. Any other
Hello,
questions
sir.
from anybody?
Hello, sir.
Yes, sir, please.
I'm Uma Mahesh. I'm a research scholar and assistant professor in VIT Chennai, Vellore Institute of Technology.
Yes, sir, please, sir.
I am also working in deep learning, neural networks, and machine learning.
Okay.
Can I get some research papers how to apply optical flow in deep learning? I
Yes, sir.
don't know
Yeah,
about.
sure,
I don't
sir,
have
sure.
idea.
What type of application you are working, sir?
Sir, I am image classification, binary classification, multi-class classification, regression analysis.
Okay, sir. Sorry, I am trying to clarify better because see, you if the data demands the motion of pixels,
I am
right?
working in images actually, digital holographic images,
Yeah,
interdisciplinary research.
understood. If that is
Uh,
demanding that motion of pixels has to be found, then you go for optical flow.
Otherwise, it is not required.
Not required. Optical flow is for moving pixels.
Okay.
I don't want to misguide, sir. So if there is
Okay.
for
I was not
example, if
having
you have
any
a
idea,
video,
sir. Sorry, sir.
no
Your
problem, sir. No problem.
presentation was nice, but the concept I was not having.
Yeah. For example, if your nature of data set says this can be a video also where I may try to understand the related frames and conclude, there you can use optical flows.
So video classification can be performed.
Yeah. Correct.
Okay.
If you have consecutive frames at time from which you want to take a decision or an analysis, there you can use an optical flow to understand how the
Okay.
pixels are moving.
Okay. I got the point.
Yes, that's my suggestion, sir. But I share the papers. If it is useful anywhere in your own research, please use it, sir.
Sir. Thank you, sir.
Yeah, thank you, sir. Best wishes.
Thank you. Thank you.
Anybody else has any questions? Okay, fine. I put my email ID in the chat box. You can also reach back to me in mail, and whatever I would like to know or clarify, I'll try to clarify with me or with my friends also. Right. So thank you again to HOD of EC department and sir for the opportunity provided from your institution side.
Sir, thank you so much for your session, sir. Valuable session.
Thank you, sir.
Thank you so much. Ma'am? Usha, ma'am?
Switch on your video. We will have a photograph with.
Vamsi Krishna?
Yes, sir.
Yes, sir. Completed his session.
Yeah, sir.
Come to ma'am.
I request all the participants, please switch on the video. We will have a photograph with the Senthil, sir.
So good afternoon and all the best to each one of you. Stay safe.
Sir, please 1 minute, sir.
Yes.
Senthil sir, thank you so much for your elaborate lecture, which is very, very useful. Optical flow is a good solution for many dynamic problems. That's a good thing. Even we can do a lot of crowd analysis. Many problems can be solved with optical flow. That's a very nice topic. Thank you so much for accepting our invitation and being a part of this FDP. As a token of gratitude, we are presenting a small digital award, sir. Please accept a digital award from our side, sir.
Yeah, thank you. Thank you, ma'am.
Please accept our thanks also, sir. We are submitting a small thank note on behalf of organizing committee and all on Vignan behalf. We are submitting a small thank note, sir. Please accept our thanks, sir.
Yeah, sure, ma'am. Sure. It's been pleasure.
Thank you so much, sir.
Thank you so much, ma'am. Thank you. Thank you, ma'am. And thank you all. Stay safe. Thank you.
Thank you, sir. Thank you so much.
So, good afternoon, all the participants. Thank you so much for your patience, listening, and dedicated concentration. We came to the almost end of the day 5. One more session was left and valedictory function was left with us in this part of a FDP. And the last session is going to start at 2:30 and 4 to 4:30 is the valedictory function, and exam will be at 7 o'clock as all of you accepted 7 to 7:30. Earlier one madam was represented, she is in travel. Madam, can you write through the mobile, since it can be written through the mobile also? Madam, are you able to take the exam through mobile? Okay, all most of you accepted. You need exam at 7 o'clock. We will follow the same time, since it is not possible to entertain each and individual's requests. Thank you. Thank you so much.
Using the same.
Ma'am, the exam will be in the form of MCQs.
Thank you, sir.
We'll be sharing some other link for writing the exam. We'll be sharing it in the WhatsApp group. So using that, you can write the examination in the evening.
Hello, ma'am.
Yeah, yes, sir. Please tell.
Sir, once again repeat, sir. Little bit disturbance there, sir. So, are you going to provide new links for examination, sir, or same link, sir? We need to follow.
Not Zoom, not through Zoom link, sir. We'll be sharing some Google form. Just as the same process daily, we are sharing the feedback link. We'll be sharing the Google form link, which you can write the examination.
Sure, sir. So, thank you.
Okay.
One, sir.
Whatever you learned up to yesterday, only that content you have to take the exam. Most analytical only, don't worry. Exam will be nice only, don't worry. If you are logically, if you are able to concentrate, it's easy only, don't worry.
Ma'am, it is possible to share all the PPTs, ma'am.
Already we are uploading in YouTube now.
Yeah, okay. You can collect from YouTube, now. Okay.
All those are presenting at a single location only. If you click that playlist you can get all at a single point.
Okay.
Any other questions?
Very good afternoon, ma'am and sir. Actually, I want to ask that the test will be there. But for Atel workshop, we have to submit the feedback form on that website. So that process also today we have to do.
It's up to you, madam. When you are free, you can upload the feedback process. You can take the feedback process whenever you are free.
Okay, sir. Okay. And the criteria will be the 80% attendance and the 60% for the quiz, na, sir?
Yes, madam. It's the same.
Okay, sir. Actually, na first day we have not, especially I have not got the WhatsApp link, so that's why I have not gone through with the link of that Zoom on the first day. That's why whole day I missed the session. In the evening, I got that in the spam, and then I just did the contact to you, and then I joined the session like that. So, is it going to be considered for me?
Have you joined through ID? If you have joined through the ID, it is possible for us. We are saving these things. From that, we can verify.
Only first day I missed, ma'am, because of the.
Anyway, after completion of each session, we are taking the snapshots.
Okay, ma'am. Okay, ma'am. Okay.
With that, we will verify. We will cross check. Please send a mail, madam, or WhatsApp
Yeah,
message.
I already sent one mail that first day I missed because of the link I have not got and
Then,
WhatsApp group.
then we will see, madam. We will check and we will get back.
Even I sent personally to the all admin personally, sir, ma'am.
Okay, okay. Madam, with
Thank
what
you, ma'am.
account you are joining? With your ID?
76, ma'am.
Okay.
Madam.
Okay, ma'am.
Madam, I have ID number 21. I have attended the first day, but somehow I could not fill that attendance link because I was not knowing that whether it will come in the chat or the WhatsApp link. But when I saw the WhatsApp link,
Madam,
it was too late and it got
today evening, we are going to send you the finalized attendance. After going through that, if you are having any submission, we will send you the Google form along with that. In that, you can represent.
I have sent a mail also to you.
We will see. Based on your representations, we will see. Okay, thank you.
As of now, we are closing the session here. Again, we'll be meeting in the afternoon session for the final thing, the final session as well as the valedictory function. The final session will be from 2:30 to 4 by Mr. Madhu, CEO of MadBlocks Technologies Private Limited. He'll be dealing with the face mask detection and sign language detection using CNN algorithms. So we'll meet after lunch at 2:30 p.m. Thank you, one and all.